All right, good evening, everybody. Thank you for your patience. My name is Dr. Brian Henning. I'm a professor of philosophy and environmental studies here at Gonzaga University, where I have the pleasure of directing the Gonzaga Institute for Climate, Water, and the Environment. We're really excited to have you again here for another in our lecture series. But before we introduce our speaker for this evening, wanted to bring your attention to the fact that we have two more events next month. The first is on April 12th, which is one of the ways that the Climate Institute is going to be celebrating the 50th anniversary of Expo 74. So this is the 50th year after that environmentally themed Expo event, World's Fair. So we'll be talking about 50 years of environmental justice in the Inland Northwest, which is apt, right? We're going to have a conversation with colleagues about the river and about enforcement of environmental laws. We'll have a keynote speaker who will be the Assistant Deputy Director of the EPA, Cliff Villa, as well as the Administrator for Region 10 at the EPA, Casey Sixculler, will both be speaking in addition to many other wonderful speakers on a day-long event on April 12th, so make sure you register for that event. And that'll be held at the law school all day on that Friday. And then we'll round out the semester and this academic year with a screening of a documentary made by our very own Charlie Pepitone here at Gonzaga. He's going to be screening his film, Without Them, I Am Lost. The one on the 12th will be available as a live streaming event, we hope, but the one on the 23rd will only be in person here in the auditorium. If you have the means, I would ask that you consider supporting our work. Not only does it make this lecture series possible, but also some of the other work that we do in the community, whether it be climate literacy work in K-12 education or climate resilience work in the community related to extreme heat and wildfire smoke. Your support makes that possible, so consider donating. This Thursday is Zag's Give Day, where we'll be having our annual fund, the university will, and we'll be looking for support, in particular for our climate literacy project. If you work with or for the Climate Literacy Project fellows, if some of you are in the room, so they're all clustered here in the middle. Some of the Gonzaga students, our climate literacy fellows, go into K-12 classrooms or K-8 classrooms and deliver hands-on climate science lessons. And so your support can help expand the work that they do every day with young people here in Spokane. And now it's my great pleasure to introduce Professor Daniel Vimont. He is most famously an alum of Gonzaga University. That's what we're most proud of. But he's also a professor of climate sciences at the University of Wisconsin-Madison with research interests that focus on mechanisms and impacts of climate variation and climate change. His work spans the development of theoretical models of ocean-atmosphere interaction, predictive models of climate variation, and on-the-ground community-based efforts at addressing impacts of climate change. Throughout his career, Dan has served as director of the Nelson Institute Center for Climatic Research and co-director of the Wisconsin Initiative on Climate Change Impacts, and in advisory and steering roles for numerous regional and national efforts for understanding and adapting to climate change impacts. As a proud alum of Gonzaga University, Dan is strongly motivated and guided by a Jesuit approach to research and education, something that I'm excited to hear a little bit more about tonight. He's the proud father of 3 children, including Gonzaga Bulldog freshman. He's an avid fly fisherman, outdoor enthusiast, and we're really excited to have him here. Join me in welcoming Dr. Dan Vimont.
Thank you. All right, thanks everyone. Thanks for coming out this evening. Let's see if this. All right. Thanks everyone for coming out. I'm going to talk today about some of the work we've been doing on looking at climate impacts and understanding how we adapt to climate impacts. And I'll talk a little bit more about that in a second here. But first of all, who is this guy in front of you in the first place? I'm the less good-looking organism in that picture there. The more beautiful organism there is a Snake River cutthroat, avid fly fisherman. I enjoy that. I'm a professor in atmospheric and oceanic sciences at the University of Wisconsin, as Brian mentioned. I love being outside. I love running, anything related to water. I'm the proud dad of 3 kids and a husband of another Gonzaga alum as well. So that's where I'm coming from. And to give you a little bit of a story about about who I am, a family story. We were driving down from northern Wisconsin one winter after skiing for a weekend. And as we're driving back home, I'm looking over my shoulder at one of the trout streams over on the side of the road, and the car is drifting into oncoming traffic. And I look at my wife and I say, "Hey, honey, that trout stream was frozen over on the way up. It's open now." When the screaming in the car stopped and we got the car back onto our side of the road, there was a couple of moments of silence in the car. And in those moments of silence, a lot of information was communicated to me. And my wife looked at me in a way that only someone who knows you really well, she kind of bored into my soul and looked at me and said, "You're really into water, aren't you?" And I realized in that moment that I had spent my entire life around the Pacific Northwest. As kids, we would go to Puget Sound. We'd go out to rivers. We'd go hiking in the mountains. Every morning here at Gonzaga, I spent 2 hours out in a rowing shell watching the vortex being shed off the edge of my oar. I went on to study ocean-atmosphere interactions at the University of Washington, and now do work on how the ocean and the atmosphere interact with each other. And so I am really into water. And in one sense, you could say that I'm an interpreter. I use tools of math and physics to interpret what the natural world is telling us. This is one example of that, and this is the last equation that I'll show up here. So don't worry, you don't need to, there's 3 people who have read this paper ever, and they're bored by it too. This is how the mid-latitudes and the tropics interact. Things like why do El Nino events start? How do they evolve? But one of the things that I've learned throughout the course of my career is that the tools of math and physics are insufficient in addressing the kinds of problems that we face with climate change. And so I'll talk a little bit about that, the additional tools that we need. I, as sort of an interpreter of our climate system, I suppose, use. So I'm going to focus on 3 things for this talk. I'm going to first set the stage and present the case for adaptation on a global scale. Then I'll move to what we've done in Wisconsin and think about how we adapt to climate change, how we've developed adaptation strategies for climate change in Wisconsin. And I'll introduce the importance of a community-based approach, a communication, a conversational-based approach for that. And then I'll go out on a limb and talk a little bit about complex adaptive systems and how a Jesuit education, I think, is ideally suited for thinking about some of the problems that we face in our world today. So setting the stage, 3 things we know about climate change. I give a lot of talks around Wisconsin, and I always start with 3 things we know about climate change, and so I'm going to start this one as well, because I think it's a good way of setting the stage. So in the role of an interpreter, I suppose, this is data here that shows carbon dioxide concentrations in our globe, or our estimate of that, over the last 800,000 years, okay? And these are actual observations. These are taken by bubbles that are trapped in ice cores in Antarctica. As snow falls, air gets trapped in between ice crystals. More snow falls, it compacts down and forms ice, and those air bubbles then are trapped in a recording of what was actually in the atmosphere back through time. And what we see is that every 100,000 years or so, if we go back in time, every 100,000 years we have more carbon dioxide, or interglacials, and then less carbon dioxide, the glacial periods, the ice ages. And keep in mind that the oldest Homo sapien fossils extend back to about 125,000 years, although there's some evidence that there might be other Homo sapien fossils back to about 250,000 or something like that. So for the history of humans, carbon dioxide concentration has fluctuated between about 175 and 300 parts per million. The last 50 years are superimposed on the right-hand side of this curve. And the last reading, it's probably a little more than that right now, but not a whole lot, is 425 parts per million. Zooming in on the last 50 years, this is what's called the Keeling curve. This is carbon dioxide measurements at Mauna Loa Observatory in Hawaii. And in the upper left-hand corner, this is a picture of Charles David Keeling. Charles Keeling started taking these measurements in 1958, and what he found after 3 years of measurements was a remarkable observation. he found that every summer, carbon dioxide concentration in our atmosphere starts decreasing, and then during fall and winter again, it starts increasing again, and we see this up and down motion. During the summertime, as photosynthesis kicks in the northern hemisphere, plant matter starts taking in carbon dioxide through photosynthesis and converting that carbon into plant matter, and so carbon dioxide is drawn out of the atmosphere. During the wintertime, that plant matter falls, decays, and releases that back into the atmosphere. We see those upward trends, that the breathing of our biosphere and these up and down trends, or these up and down fluctuations in this curve. And after 3 years, he could have stopped taking those measurements, and that would have been an amazing result. But he continued, he persevered in taking these measurements, even when he had to be encouraged by other scientists to continue taking these measurements. And gradually, through time, we now have what's probably the most iconic piece of evidence relating to climate change, which is now referred to as the Keeling curve. And it tracks the long-term increase in carbon dioxide in our atmosphere. One of the few things we've known about climate change for several decades now is that that long-term increase is anthropogenic, is due to humans. And we can look at, we can use several pieces of evidence for that. Currently, we can use inventories of fossil fuel emissions, but before that was available, we could use carbon isotope records to show that this was anthropogenic in origin. When I look at this curve, let's see, I was born at 332 parts per million. I graduated from Gonzaga here somewhere around 360 parts per million. My kids were born at 382, 383, 398 parts per million. And then in April 2014, as my daughter celebrated her first birthday, we passed 400 parts per million for the first time in the history of humans. That's a remarkable statement, but what's more remarkable is what happened 17 months later. We passed 400 parts per million. The Earth inhaled, exhaled, inhaled, and then 17 months later, in November 2015, we passed 400 parts per million for the last time. No one on Earth will ever experience carbon dioxide concentrations below 400 parts per million. In 3 or 4 decades, when we pass 500 parts per million, it's very likely that we'll say the same thing. That's a reality that we will have to live with as we move forward. The second thing we know about climate change, our world is warming. This shows a time series of global temperature over since 1878 to 2023. And everywhere there's a red bar is a year that was warmer than the 20th century average, or where there's a blue bar is a year that was colder than the 20th century average. And we can see that the spikes in this record, the biggest spike is this last year, 2023, and that's due to the big El Nino event that we're having right now. It's currently decaying. It's not as big as the 2015-2016 El Nino event, another spike. The 1997 El Nino event, 1997, 98, and 82, 83 El Nino event. And so those fluctuations in El Nino events, El Nino is the biggest thing that can naturally happen to our climate system on year-to-year timescales. And it tends to warm our planet by a couple tenths of a degree each year that we have an El Nino event. On longer timescales, we're seeing a larger trend. And that trend, that upward trend, that warming that we're experiencing is due to the carbon dioxide that we've put into the atmosphere here. Putting this in context, 1997, 98 was the warmest year in the 20th century. Moving forward, we will never again experience a year that was as cold that is as cold as 1997, 1998. Moving forward, that's a reality that we're going to be living with. Putting that in historical context, the third thing we know about climate change, and this is, we've known this for a while, although probably not this long. I like using the quote though, is that these two are related. Carbon dioxide and temperature are related. And there's a variety of things we can do today using more modern analyses than this. But I like this quote. This is a quote from Eunice Foote. This is the first paper published by a woman in physics, by an American woman in physics in 1856. I think there were 12 or on the order of 12 articles published in Physical Sciences by women in the 19th century, and Eunice Foote has like 7 of them. So she published an article looking at how different gases absorb energy and warm up, and found that an atmosphere of carbon dioxide would give to our Earth a high temperature, and if the air had a larger proportion than at present, an increased temperature. So this is the first documentation of someone identifying the relationship between carbon dioxide and global temperature. John Tyndall repeated these experiments a couple of years later. It's not clear whether or not he was aware of these. She was not allowed to present these. Her husband had to present these results. And so her work was largely forgotten until recently. And now there's obviously, now we're making more of an effort to give the credit due to her. Moving forward, what do things look like moving forward? Well, we can use global climate models, and that's the sort of stuff that I do in my day-to-day job, I suppose, is running these global climate models. We can run them forward to get a sense for what our world will look like in 50, 100 years. And the problem is that we don't know how our global society will evolve. So we can take these climate models and we can apply changes in carbon dioxide to these climate models and look at what the climate models tell us will be occurring. We don't know how our global society will evolve, so we use different storylines. And so this red storyline here is kind of a business as usual type storyline where nobody gets along, there isn't any sharing of technology, we stick with a fossil fuel-based economy, population peaks late in the century. And this red storyline, we end up with about 4 degrees Celsius warming by the end of the century. This blue storyline is one where we rapidly move away from a fossil fuel-based economy. Population peaks early in the century. We share technology, and so forth. And that levels off at about 1.5 degrees Celsius of warming. The big difference between these two, in my mind, is the fact that this one levels off. This one doesn't. This continues to warm. In reality, neither of these are likely scenarios. We're already past this scenario. And this scenario will probably be uneconomical to extract that much carbon from fossil fuels. So we're going to be somewhere in the middle here. The good news, by mid-century, it doesn't really matter what storyline we're on. We kind of see the same amount of warming by mid-century no matter what. What that means is that the decisions we make now have an enormous effect by the end of the century. And so we should definitely be acting now. But it also means we can be planning for what we know is coming. And that's what we're doing. So when we talk about what we can do about climate change, we usually talk about mitigation and adaptation. Mitigation is some sort of activity that we would do to try and reduce the amount of climate change that's going to occur. Adaptation is recognizing that a certain amount of climate change is inevitable, and we need to be planning for that already. And that's what I'm going to talk about mostly today. So around this point, when I'm giving my lecture to my 101 class, I usually, after the whole, statements about we'll never again see climate, CO2 below 400 parts per million, all that. I don't mean to be flippant about that, but there's a lot of stares, sort of like hollow stares, and it feels rough. And so I usually say, keep in mind that you will fall in love in your life. You will be amazed at the kindness of strangers. You will be blown away by the beauty of nature. All of this will continue to happen, but at the same time, we have a very serious issue that we need to be dealing with. And so our lives are complex. So the second thing I want to talk about is climate change adaptation and how we've addressed some of that in Wisconsin. Hopefully, I've made the case that adaptation is something that we can and should be doing, and it's actually the most predictable signal in our geophysical system right now is this warming that we're experiencing. So in Wisconsin, we started a group called the Wisconsin Initiative on Climate Change Impacts. And so in 2007, a bunch of scientists from the Department of Natural Resources and from University of Wisconsin got together and started talking about what does climate change mean for the way that we manage our natural resources. We had a conference, and after the conference was done, we said, hey, we should do this more often. There's a lot of opportunity to better understand climate impacts in Wisconsin. And so a prospectus was sent out describing how we would set up this organization, and it read as follows. It said, climate scientists will run climate models forward and tell us what the climate will look like in 2050 and beyond. They'll pass that information on to ecosystem scientists who will run that through their models and take a look at how our ecosystems respond. They'll pass that information on to policymakers who will then make good decisions. Right? And about 5 minutes after getting this email, I got on the phone with Chris Kucharik, who's in the agronomy department, and I said, we got to derail this immediately, because that's not what happens in reality. What really happens is climate scientists tell you what they think are important. Ecologists say that's not what we needed, and the process is over, and you're done with moving forward. And so instead, we put together an organization that operates as a conversation. They said what really needs to happen is there needs to be conversation between all of these different interacting components in order for us to make progress on understanding what's needed, what information is relevant, and how we come up with research that can advance our understanding of climate impacts. And so WICCI sits in between this realm of science and climate solutions, and its mission is to generate information that can foster solutions to climate change in Wisconsin. Note that we're not advocating for different solutions. We're working with people to try and identify how we can produce information that advances solutions. That's an important step there. So if you're like me, you love looking at org charts. This is WICCI's org chart, and this is my favorite org chart. WICCI is set up as a decentralized network. It's set up as an open decentralized network, kind of like Wikipedia or Napster or some of these other decentralized organizations that you might be familiar with. It brings together people from all different sectors, public and private, decision makers, scientists, and enables planning and investment. So within about 3 years, WICCI had grown from an idea to about 250 people around the state contributing in some way to understanding impacts to a wide variety of sectors in our state. Over 70 different organizations participating in some way to understand how climate change affects their work. WICCI's set up around working groups. Here are the current set of working groups. And again, the idea is to foster conversation between working groups. And I want to give some examples of how that conversation is important and what it allows us to do. All right, so despite me saying that this linear sequence of events is not the way things work, one of the first things we did in WICCI is recognize that climate data was needed. And the problem is that global climate models at the time, this is the typical spatial resolution of a global climate model. So global climate model, we solve equations that govern how our climate system works, things like conservation of energy, conservation of mass, the Navier-Stokes equations. If we write all these equations out, they're not solvable. We can't come up with x equals 42 at the end of looking at the end of these equations. And so what we have to do is we discretize these equations. We divide the world into boxes, and we allow the boxes to communicate with each other in different ways. This is something that I did when I was here at Gonzaga. I first started looking at these grid point models of atmospheric circulation. The problem is that the more boxes we have, the longer it takes to run these models, and they already take months to run on the world's fastest supercomputers. And so we have to have pretty coarse resolution boxes. That's not the kind of resolution that people need, though, to make decisions about climate impacts. And so coming up with some sort of a regional scale climate data was identified as a priority. And so we submitted a proposal to develop these regional climate projections. And it takes a couple of months to evaluate that proposal. In the meantime, we had all these conversations with different groups in WICCI. The proposal was funded, and we realized I'm going to get to this in a second, on the first day where we decided to embark on doing the work on this proposal, we sat down. It was a September morning at about 9 o'clock, and by 9:15, we had looked through the proposal and realized that what we had proposed would not meet the needs of the people in WICCI and what they needed out of climate data. So we scrapped the entire methodology and came up with something completely different. So to give an example of why that's important, this is what happens if you just use basic interpolation. So across Wisconsin, across Washington, across the whole US, there's different observing stations. You can see where the observing stations are by these little dots here. I'll explain why in a second here. And if you just, every day someone's going out and they're measuring the maximum minimum temperature that occurred over the last 24 hours. If you just take that data and you interpolate it to a grid, then what you get for the mean precipitation in Wisconsin for July looks something like this. It's a little splotchy. I don't necessarily believe all the details, but wet, a little wetter in the southwest is true, and a little drier in the northeast is true. This shows the fraction of wet days. So if you want to interpret this, this is the probability that rain will fall on a given day. If you want to interpret this in a different way, if you would like to go on a picnic in Wisconsin, what this tells you is that you should find an observing station, because your odds of getting rained on at the observing station is far less than if you're far away from an observing station, right? This is the extreme rainfall in Madison. And what this says is that, well, you've decided to go on a picnic and it's going to rain. If you don't want to get really wet, you should go as far from an observing station as possible, because the extreme rainfall is smallest when you're far from an observing station. What is this? Why is this the case? In this case, if it rains at one location and doesn't rain at another location, it rains everywhere in between if you use standard interpolation techniques. If I have an extreme event at one location, the odds of it being an extreme event at another location is actually pretty low. And so I mute all the extremes in between. And so the methodology that you use, this may seem like just sort of a you know, oh, that's interesting. If you're a forestry scientist, this makes a big difference. Constant drizzle versus realistic rainfall has a very different effect on the way you interpret results. So we produced this data, and we started working with people in WICCI. And we'll give a couple of examples of some of the things that we did here, some of the results. This shows the change in wintertime temperature in Wisconsin. And this is the historical data, which shows that wintertime is warmed by about 6 degrees Fahrenheit over the last, we use Fahrenheit. As a scientist, it's always a little jarring, but we give a lot of public talks, and so Fahrenheit makes more sense. So Wisconsin is warmed by 6 or 7 degrees Fahrenheit since mid-century. That's wintertime nights. If you've experienced wintertime nights in Wisconsin, you're thinking to yourself, hey, climate change sounds like a good plan so far. It can get very cold there. And here's the expected change in the wintertime. We expect a warming of an additional 5 or 6 degrees by mid-century. So again, this is leaving me a little unsatisfied here because I don't know what it actually means, right? A change in temperature, well, how does that translate to something that actually matters? And so in conversation with Ned Zielsdorf, who's the director of the American Birkebeiner, anybody ski the Birkebeiner or know what the Birkebeiner is? All right, have you skied it? Oh, okay, the American Birkebeiner is the largest cross-country ski race in North America. And it's run out of Hayward, Wisconsin, which is like in this area up here. And so I was talking to Ned Zielsdorf, and I said, hey, we've got these projections, these climate projections. We can start looking at what snow conditions will be like in late February when the Birkebeiners run. And Ned says, that's not what we need, because we don't actually care what the snow is like around that time, because we can always adjust our race. We can change the route. We can plan for bringing in snow. We can do something else to deal with that. What we really care about is the condition of the snow season in southern Wisconsin and Minneapolis. Because if the snow season's good in Minneapolis and southern Wisconsin, then people will train for the race, and then they'll sign up for the race. And so that's the key metric that we care about. That changes the way that we analyze data. It gives us a guidance for how we would analyze that data. So this is the American Birkebeiner. This year was the warmest year. This winter, this February, is going to be off the charts in terms of warmth for Wisconsin. And the American Birkebeiner had to be fundamentally changed in the way that they ran that due to the lack of snow. Winter warming also produces less extremely cold days. So this is the number of days per year where temperature gets below 0 degrees in Wisconsin. And so if we take a look at that number, it's about 20 days per year in Madison where the temperature is below 0 degrees Fahrenheit, which either sounds great or horrible to you. And that's expected to decrease to about 5 or 10 days per year, so a drastic decrease. What does that mean? This is Marshall Pecor. Marshall is a forest manager in Menominee Nation. You can see Menominee Nation's boundaries from space because their forests are so well managed. Their sustainable management practices are so, they're emulated around the world. People fly from around the world to learn from them. The lack of really cold nights means that there's a larger chance of infestation, or a larger chance of pests overwintering, and infiltration of bugs that will hurt these, that will destroy stands of wood. They're concerned about this because forestry is an important resource for them. The other thing that happens in Wisconsin is that in wintertime, forestry practices can only occur on frozen land. And so if the ground isn't frozen, then you've got to build gravel roads, and they're already building gravel roads and adapting to climate change in northern Wisconsin as a result of these things. So adaptation strategies, I talked about a couple of them with the Birkebeiner. We're already in Wisconsin, adaptation to changes in the kinds of conditions on the ground are occurring. For forest management, foresters are working with the Department of Natural Resources as well as the Northern Institute for Applied Climate Sciences around the state to try and identify ways to change the management of forests, perhaps growing species that are more likely to be climate tolerant over the next 60 years, growing in ways that we might buffer forest stands from invasive species, thinking about harvesting practices in different ways, and thinking about the interaction between forests and the wildlife that they support as well through WICCI. Climate adaptations in the forest stands that also are benefiting wildlife. That conversation extends beyond just sort of climate and climate scientists and people who are using the data. An example, summer warming. Winters warm more than the average, summers warm less than the average. So this is a change in maximum temperature in Wisconsin. We see maybe 2 or 3 degrees Fahrenheit warming. This is a brook trout. This is one of the native, the only native trout in Wisconsin. So the Department of Natural Resources has to manage for these brook trout. And so warmer stream temperatures, brook trout start dying when the stream temperatures get warmer. As a climate scientist, I figure this is due to dissolved oxygen in the water. The colder water holds more oxygen than warm water does. And so I always assumed that fish would start dying because there was less oxygen. It turns out that it's not that, and Matt Mitro, who took this picture, I'll show in the next slide, Matt Mitro informed me after I answered some question saying, oh yeah, it's just the dissolved oxygen in the water. He said, actually, it's not that. It's the fact that, and here I'm stepping way out on a limb here, probably everyone in this room knows more about fish metabolism than I do, but the enzymes that fish use to process food into energy start unraveling when they get too warm. And so I'm glad I'm getting a nod over here, which tells me that I'm not completely off base here. And so they can no longer produce energy. Above about 74, 75 degrees Fahrenheit, brook trout have a couple of minutes to live before they can no longer survive that. That changes the way we manage creeks. This is Matt Mitro. Matt Mitro did a lot of this work. He took this information and they looked at, they used a triage approach and looked at streams that would support brook trout, streams that definitely would not support brook trout in the future, and then this middle zone of streams that they might be able to do something to help support brook trout. He then went out to the driftless area, which is the southwestern part of our state. Trout fishing is $1 billion industry annually in southwestern Wisconsin and the driftless area. And talked with people in the driftless area to identify priorities for conservation. Again, a communication approach, working with people who lived in the region to identify which streams should they be devoting resources to in order to better protect trout habitat. Last example I'll give here. So again, conversation allowing us to identify solutions that emerge from the people who are involved in that conversation. It's not a prescriptive approach. We're not saying, you know, this is what needs to happen. We're setting up an infrastructure that allows that to happen. Last example I'll give here, extremely hot days. Currently, we only get about 10 days per year where the temperature gets above 90 degrees in Madison, and that's expected to triple by mid-century. But it turns out that hot days are not nearly as important as warm, hot nights. And so currently, nights in southern Wisconsin, say Madison here, where temperature gets above, or where the temperature stays above 70 degrees, we usually get about 4 or 5 of those days per year. That's expected to quadruple by mid-century. That's a big deal because at night, if you can't cool off at night, then you don't sleep well at night. Anybody ever experienced that on the really hot, especially hot, humid nights, which is what we experience in Madison? The humidity is a lot worse than around here. If you can't sleep well, it exacerbates all kinds of other conditions. Asthma, heart disease, elderly are far more susceptible to nighttime heat than daytime heat. More people have died from heat waves in Wisconsin than every other natural disaster combined. And so understanding a daytime heat wave is very different than a nighttime heat wave. In the daytime, you can potentially go to a coffee shop. You can go somewhere that's open, right? There are shelters that you can go to stay cool. At night, you got one choice, and that's to go home. And if you don't have resources to be able to fight that heat, then you're far more susceptible to those kinds of events. And so we work with the Department of Health Services to identify ways to work with communities around Wisconsin. One thing that we find there in Wisconsin, this is a climate health vulnerability map for the Milwaukee area. On the left, or where it's dark red here, is a region that is especially susceptible to heat. And everywhere where it's a little, these yellow areas are less susceptible to heat. So on the left is the current climate health vulnerability map, and on the right is the historically redlined areas in Milwaukee. And so we see that where we are currently vulnerable to heat are regions that historically were redlined. If you're not familiar with redlining, redlining was a practice that was a federal policy where communities that were redlined, or that you draw these lines around different communities, and if that line, you know, the red one, meant that you were not allowed to invest in those communities. And race was used as one of the criteria for whether or not you were allowed to invest in these communities. And so if we look at current heat vulnerability, a lot of this is occurring due to the lack of the ability to grow an infrastructure, to be able to invest in putting in a supermarket, or community structures that produce more resilient communities. So that history is important there. Department of Health Services has developed a wide-ranging set of materials for public health officials around our state and in educating people on how to deal with potential impacts, not only of extreme heat, but changes in changes in disease vectors, more Lyme disease, that sort of thing. Turns out the mosquito that hosts the Zika virus will be able to overwinter in Wisconsin in a couple of decades. These kinds of things to try and educate health officials around the state. So what I've shown here so far is a bunch of examples of how working together allows us to come up with things that, as a climate scientist, I don't know anything about how public health officials do their work. I mean, I don't know anything about how enzymes work. As that should be obvious. I can't even express it here. I'm using, like, I don't know anything about the American Birkebeiner other than it's a ski race in northern Wisconsin. But in conversation, once we set up that opportunity for the conversation, we can start converging towards solutions. We start, new ideas emerge. So I want to end, the last section I want to talk about here are analogies between complex adaptive systems and a Jesuit approach to institutional change. And this is also titled, Where Dan Really Steps Out on a Limb. Keep in mind that my research is how two fluids on a rotating sphere interact with each other. And so when I'm talking about this, I'm kind of stepping out on a limb. But it's something that I've read about a lot and I've looked into in directing WICCI. I started looking into the literature on complex adaptive systems and looking at structures in complex adaptive systems and how we think about instigating change in a system that is complex. So let me start off by, what do we mean by complex adaptive systems? So complex adaptive systems are often, the first thing is they're very difficult to talk about because guess what, they're complex. It's very hard to reduce, they're irreducible, and so it's difficult to talk about them. So oftentimes it's better, you identify these better by just sort of using examples. So complex adaptive systems involve numerous interacting agents, and those can be socio-ecological agents. So in this image here, think about these black dots over here. Think of each one of these black dots might be you. It might be some other people. It might be the landscape that we live with. It might be the Spokane River. It might be fish, right? There's all of these different agents that are interacting. You interact with each other. You also interact with the fact that there's a river there. It informs how you make decisions. The things you like to do. If you like going skiing, you know, you're connected to Mount Spokane. You know what Mount Spokane is. It affects you in some way. It affects the decisions you make. And so complex adaptive systems are these systems where, especially socio-ecological systems, that are highly connected and interacting. Complex adaptive systems typically are path dependent, meaning history matters. So think about the history of you know, this idea of historically redlined areas, the work that's been done here with the Beat the Heat work, and looking at, by the Climate Institute here, looking at impacts of heat waves here in Spokane, and understanding how the history of how Spokane has developed impacts the way that Spokane is affected by heat waves. They exhibit emergent behavior. Emergent behavior is behavior, if you study each individual component of a complex adaptive system, you won't necessarily be able to infer, oh, this is how the system will act as a whole. Think about swarms of birds, right? You see these giant sort of structures that kind of evolve. If you were to study one bird, you wouldn't necessarily think to yourself, oh, that's going to produce all of these interesting swarm-like behavior. And the other one is that they operate far from equilibrium. What does that mean for practical purposes here? Let's think about definitions of sustainability. In your head, think about what you think of as sustainability. I think oftentimes the simplest definition is one where we have a steady state, where stocks and flows are balanced in such a way that we can maintain a current state. But if you're constantly far from equilibrium, that's not a reality. If you adjust the system adjusts to whatever forcing or alteration in that system is imposed. And so complex adaptive systems operate far from equilibrium. There's a lot of good examples of this. One would be you know, the internet, right? The way we interact with the internet and the technological human interface there. It's constantly evolving. Our economy, Spokane is an example of a complex adaptive system. Climate impacts in Wisconsin are an example of a complex adaptive system. How do we set up structure within that complex adaptive system to try and foster some sense of sustainability? This is a lot of words here. I know everyone always says don't put a lot of words on your slide, but this is one of my favorite quotes about thinking about sustainability and how we've designed WICCI. In complex adaptive systems, sustainable management comes close to initiating a co-evolutionary dialogue where a continuous learning process is driven by the mutual and reciprocal interactions among the interlinked subsystems and agents. That's a mouthful, but let me give an example of that. You and someone else show up at a party and you have no idea who that person is, and you don't know anyone at the party, and so you start talking to somebody about something. And usually you converge around what's called a boundary object in social sciences. And weather is the perfect boundary object. Like, hey, it snowed today. Were you affected by the snow? The two of you can relate to that object. And by being able to relate to it allows you to start that communication. But what happens is that communication, in that interpersonal communication, begins a new process of coevolution. that pretty soon you're talking about new things, and pretty soon you're learning from each other, and you're talking about new topics that neither of you would have had any knowledge of, or neither of you would have talked about or had some context for, except for the fact that the two of you have started that interaction. That's coevolution. In complex adaptive systems, a learning network fosters that coevolution. And so what WICCI does is it sets up this blue mesh within this complex adaptive system. It sets up the infrastructure that allows people to start that communication. And through that communication, we all co-evolve together in ways where we're identifying emergent properties, we're identifying new research that needs to happen. That communication tells us, it directs our research, it directs us to producing relevant research. And in that communication process then, that organization, that structure, allows catalyzing the emergence of new ideas. So that's why we've set up WICCI. In my mind, there's a strong similarity between, there's a parallel between this kind of a system and this kind of organization in our Jesuit background. And here's where I'm going out a bit on a limb here. But if a coevolutionary dialogue is what we are aiming for in this, and how does our Jesuit education, how does a Jesuit philosophy impact the way we think about that? The Ignatian pedagogical paradigm, we bring unique perspectives of context. It can be summarized, I suppose, in the 3 words: experience, reflection, and action, and oftentimes put context and evaluation on this as well. We bring unique perspectives. In a complex adaptive system, I hope I've shown that each of us brings a unique set of skills, our own background, our own context that informs who we are, and it's through that conversation, it's that context that you bring to this that allows us to start communicating and allows us to identify how to move forward in coming up with new solutions to problems. This idea of experience, learning through our lived experiences, experiencing together. Again, this idea of working together. Reflection as the embodiment of learning, reflecting on what we see and thinking about how that meshes with our own internal experiences. Critical thinking, being open to that critical thinking, being open to thinking about how our situation, how we respond to that. And then action. I think that this is probably the clearest example of actions are motivated by and for others in this case. A Jesuit perspective on this, I think, this idea of more, magus, this idea of our actions are motivated by a greater good. And ultimately, in WICCI, this is why we set this structure up. We understand there's a greater good. We don't know how to get there, and we can't prescribe the particular decisions that people are going to be making, but we know people are going to be affected by climate change. And so we set up a structure that allows that to emerge, allows solutions that are relevant for people to emerge through those interactions. And then evaluation, this idea of, again, of more. Not only evaluation to say, hey, did it work, but what are we missing? What can we do more? What are the new areas that we need to be thinking about? How do we think, how does what we've learned here impact another area? Constantly thinking of that learning process and interacting with each other to try and advance these climate adaptation for, in general here. I feel like I'm a little out on a limb here, and the best examples I guess I had of thinking about how a Jesuit perspective influences us there were actually through, I sent some friends of mine some text and said, hey, how does Jesuit education, how do you think about that with like a systems-based approach to complex adaptive systems? And I heard a lot of interesting examples. Matt Brindeville, who graduated in about the same time I did, talked about Laudato Si and the recognition of our connection with the environment. This idea that we are connected not only as humans, but we are also connected with the environment. Our decisions are impacted by our our land ethic, and the way we treat the environment affects us as well. I think nation pedagogy and thinking about how we discern that relationship, how we critically think about that relationship and the decisions we make has been influential for him. Talked with Andy Shields, who after leaving here, went to Seattle and had this idea that the way humans interact with technology was going to be a big deal. And so he contacted folks at ESPN and said, I think this is a thing here. And so they gave him 6 months and an intern, and he came up with and developed ESPN Mobile as a result of that. Thinking about how people interact with technology before there was any, this was back when cell phones, you'd have to it's like 50 cents a text. You'd have to press 33355, to text anyone. But already thinking about the way that things were moving. His latest endeavor was working with BP to develop infrastructure to allow the development of digital twins for BP operations. And when he was talking to me about starting that job, he was conflicted about working for BP. But what set him over the edge on this was the recognition that by setting up this infrastructure of their operations, that would allow them to more efficiently use renewable resources and potentially achieve 40% renewables in their inventory in the next couple of decades. Thinking of what he's actually doing, but that's underpinned by a desire for the greater good. I talked with my wife about this, Mandy. Mandy talked about developing a cardiopulmonary rehabilitation program for one of the larger hospitals in Madison. And she talked about using a whole person approach to that, bringing together dietitians, cardiologists, physical therapists together in more of a combined effort to deal with specific problems that people dealt with in cardiopulmonary rehabilitation. Again, at a level of thinking about the systems that sit in place, but also on an individual level, talking with individuals and recognizing where their background comes from and being able to tailor specific care based on where people were coming from, where that interpersonal human human interaction. These are all examples of how people have used this Jesuit education in these systems that are inherently complex, I think. My favorite quote was from John Giles. This is a text. He actually texted this to me. In my view, systems thinking is a lifestyle, not a checklist. The Jesuit core curriculum programs that lifestyle into our brains if we are open to it. The people who taught us modeled that lifestyle through living a humble, truth-seeking life. Add it all up, and we are equipped to deal with complexity and ambiguity. I hate reading these things, I apologize, but it's what I'm doing. So, ambiguity, because we've been taught how to have an open mind, how to delight in learning new things. I love that quote. We've learned the discipline of working with structured, logical thought. We've learned how to interrogate our theories and apply rational, critical thinking to make them better. It's a mindset that is more than a set of bulleted slides, which is why, inevitably, I'm going to fail in trying to explain these complex adaptive systems in a talk and a series of bulleted slides. But it's also why, probably, through our Jesuit education, you recognize what I'm talking about in some way. You can find areas to grab onto and say, that makes sense. Ultimately, throughout all of this, I am drawn back to this Keeling curve here, this curve of carbon dioxide. All of us are connected in this curve in some way. All of us have contributed to this curve in some way. Everything we have done as a global society to reduce climate change is reflected in this curve. People have referred to this as relentless, the constant increase in carbon dioxide in our atmosphere. We are also all connected because all of us are going to be impacted in individual ways by climate change. And all of us have individual things that we can be doing to reduce this and to adapt to climate change as well. Ultimately, this idea of interconnectedness, I think, kind of underpins the way that I think about how climate change affects us. This connection with the environment, the connection with each other, and ultimately, this is why we do this. Thank you in advance for what you will do to advance the greater good in our world.
All right. Ooh, apologies for that. So we might have some time for questions if anybody has any. And also, if you're at home and like to ask a question, you can email me at climateinstitute@gonzaga.edu, and I check my phone every now and then. It's a really interesting talk, mixture of science, and then I love the going out on a limb at the end here and lack of your comfort zone. And I'm curious, especially to maybe hear from a Gonzaga student or two first, if there are any questions. Yes, so if you could introduce yourself before you ask.
Hi, I'm Grace Fletcher. I'm a senior environmental studies major here. Oftentimes I feel like, obviously we know that working towards climate solutions and climate adaptations is extremely important given that we already have messed up enough that we're going to be facing some of our own repercussions before we can change them. But oftentimes I feel kind of defeated because adaptation and solution feels like more of a reactionary measure than preventative. And I was wondering if you ever feel that way, and if so, how do you kind of combat that feeling?
That's a great question. Thanks for that. That's a very real feeling there. I would say that I recognize that both are inevitable, that we need both. I focus on adaptation here for historical reasons. There's a story as to why we only focused on adaptation to begin with in WICCI, and now we're focusing on both adaptation and mitigation. There's politics behind that as well. To me, it can be very disheartening to look at some of these projections. The other side of that is there's that conflict in me, right, in all of us. Like, in one sense, it's very disheartening, but in the other sense, boy, I love the natural world. I love applying math and physics. I love understanding stuff. It's like a puzzle, and to me, there's joy in that. There's beauty in that. The other thing that is incredibly uplifting to me is the fact that as part of thinking about adaptation and setting this up, I get to connect with people in ways that I never would otherwise. Talking with Jeffrey Mears in Oneida Nation and learning about the history of their people and how their priorities for natural resource management or for maize growing. Thinking about how Bad River and northern Wisconsin, the Native American nations in northern Wisconsin, the way they interact with natural resources, it's a different value system. And being exposed to that is beautiful. In a sense, there's joy in thinking, oh, here's how one might come up with solutions for these sorts of issues. So it can be kind of defeatist in a sense, but in the other sense, it does bring us together. It's kind of my hope that's what happens with climate change, is that it is a chance for us to come together. I think oftentimes we talk also about the impacts or how much money it's going to cost or all the bad parts of it. There are tremendous amounts of opportunities in building a clean energy economy. There's tremendous amounts of opportunities in thinking about how we adapt to our changing climate as well. And it's a reality that we have to deal with. So I'm mixed. It's a good question. I don't have a good answer for you aside from saying both.
You were talking about some of the challenges of Wisconsin. I'm thinking of the slide, and I've taken your computer back, so you can't jump back. But when you're talking about the different fisheries and the rivers that were going to be sort of savable and ones that weren't, and several times throughout your talk, you were talking about the idea of facilitating conversations and then the emergence of solutions. And what I was imagining in that conversations was some people are being told that their rivers are not savable. Others might be savable. And I'm just trying to imagine how a conversation would go that would just, solutions would emerge. It sounded like a little bit of like fairy dust took place. And then
it could be a little bit of fairy dust in there as well.
Say a little bit more about, because we also are in a very similarly politically complicated environment in Eastern Washington. We've got a lot of similar sort of challenges. When you imagine facilitating a conversation where you're delivering difficult sort of information, you're providing facts as you understand them, but then
Yeah, how do you deal
How
with
does,
that?
how do solutions emerge exactly? Where's the pixie dust?
Yeah, so in that particular example, what was done was the Department of Natural Resources went out to the driftless area, and they gave everyone monopoly money. And they said, all right, we've got a certain amount of money to spend, put the money on the creeks that you're interested in, and then we'll discuss, keeping in mind the fact that some creeks are not going to support brook trout, period. Some are going to be okay, and some are going to be in the middle there. The other part of that is that not everyone is interested in preserving brook trout, right? There's plenty of farms in the area that would be more than happy not to have to deal with the buffers and so forth. But there's also a history of interaction between the agricultural community, land trusts, tourism industry there. And so,
I mean, I guess another way of putting it is there have to be a baseline fund of goodwill that you're drawing on, or are people all, because they don't sound like they're coming from the same perspective, they don't sound like they're all have necessarily the same values or commitments, and yet you're still able to have solutions emerge?
yeah, this is a good question. I don't have a good answer for this one. In that case, this was directing the DNR's master planning process. The master planning process determines how the state spends money on conservation activities here. And so, yeah, some streams are not going to be savable in that sense, but it doesn't mean that they're not going to be fishable, right? Brown trout is another, and so there are other options there. It's not necessarily a binary outcome in that case. But in general, you're raising a good question here. Where's the how do we deal with conflict in these sorts of things? I don't have a great answer. A lot of the things that we look for are win-win type situations where when you start looking at problems, you start realizing, oh, doing one thing can actually create sort of a win-win-win situation for people when you're having those interactions.
We were having dinner before this, and I was pushing Dan on this as well, and so there's a sense in which the work that you do, it sounds like you're presenting, and you had the beginning of sort of presentation of two boxes, and WICCI was in the middle of them, right? And sort of in this sort of value-neutral position of providing helpful information. But then throughout, you're also talking about the emergence of solutions, and then at the end, very strongly, in talking about the common good. And so there seems to be a very clear value positive statement about the way you approach what you think a good solution would look like, or what you want to help emerge.
I don't think that's actually...
Is that not true?
Yeah, I think that's maybe pushing that a little far. What we do is WICCI is focused on producing scientific information that allows people to converge towards solutions. Not WICCI to converge towards solutions, allows people. And so oftentimes what we'll do is we'll work with, let me give an example of that, I guess. Madison Metropolitan Sewerage District is interested in combined sewage overflows, and so they care a lot about these extreme rainfall events and how to manage their storm system for that. Our contribution to that would be to say, well, we recognize that you have a certain set of models that you're using. What's the information we can provide that would allow you to run those models and try and identify how to reduce these combined sewage overflows, which I would call a good solution. Reducing, human waste that just sort of flushes into the Great Lakes, I would call a good solution. But I'm not necessarily advocating for anything there. We haven't had anyone sort of approach us and say, hey, I'd like you to produce some climate data that allows me to completely destroy the environment over in this area. So that's been, we haven't had to deal with that kind of a situation.
I'm glad they have not found you
yet. Yeah.
Other questions? Got the fellows. I'm going to wait for just a second. One more student, and then I'll get you, David.
Yeah. Hi, my name is Georgia. I'm a sophomore environmental science major. I had a question, or just, could you give advice to students in the crowd who are interested in going into the climate sciences field after graduation? Like, how did you get there? Do you just have any general advice for students that are looking to do that?
Yeah, that's a really good question. It sort of depends on what area you want to go to. There's a variety of routes you can go. For me, I'm very math and physics oriented, and so I went into atmospheric sciences atmospheric and oceanic sciences and started doing more theoretical work. That work, after developing that base, I started getting into climate impacts by looking actually at food security in Indonesia. And so kind of came into that in a very different approach. In terms of moving forward, think about the kind of directions you're interested in. Are you interested in more of a pure math? There's a lot of directions you can go, right? Pure math, physics, climate science. You can go to ecological processes and thinking about botany departments or more of the ecological impacts, forestry, wildlife. If you're interested in public health, there's aspects there as well. So kind of however you're kind of moving in that direction, think about like things you can do to kind of enhance that. As a sophomore, I would say start talking with people who are doing work, like sustainability work. Things like going and meeting people for a half hour and saying, hey, what do you do? Why did you get into this? There's a lot of resources online for how you approach those kinds of conversations. And that'll start honing how they ended up getting into their jobs and how they managed to, it also starts setting up networks for you. If you can get involved in any sort of research or any sort of field experience, that's really useful. There's a lot of these research experience for undergrad programs through NSF, there's a lot of these research opportunities. Gonzaga has made one of their strategic priorities, at least in a few years ago, was to try and get students into more of these research. That's transformative, and I think really look for some sort of opportunities there. Beyond that, think about, there's so many directions you can go there. You can go into climate communication, in which case my advice of getting a physics degree is useless, right? But there's also, that's never useless. I'm looking at Eric Kincannon back here who's glaring at me right now. I'm like, no, it's always a good idea. But think about also ways that you can broaden your experience here. Also, take advantage of what you are learning here. You're getting a broad education, which is something that a colleague of mine who works in hydrology only takes grad students from liberal arts institutions because he needs people who can think broadly. Use that. Think of the kinds of transferable skills that allow you to communicate with people in different subjects, that allow you to recognize differences in value systems and respect those value systems. These kinds of transferable skills that you're getting in a broad liberal arts education here, I think. I don't know if I kind of punted on the first part of that, but I hope that helps.
Thanks for a great talk. This is fascinating. If you wouldn't mind, though, could you return to the mechanics of climate change a bit?
Yeah.
And I know you've done a lot of work in atmospheric, oceanic interactions. I'm really curious about what drives the ENSO cycle. And you brought up El Nino earlier.
Yeah.
Can you speak to the
man,
causes
I'm
behind the
glad you asked.
winds that then push the oceans and drive the whole thing?
Yeah, I can. So that's my bread and butter research.
Did you bring him with you,
There's
Dan?
a plant in the audience here, folks. I'm warning you ahead of time. So El Nino events occur. It's a warming in the equatorial Pacific. And so in general, in the equatorial Pacific, man, it's the wrong guy to ask that question here because we're going to be here. We'll break for dessert here in about an hour, and then we'll come back, and I'll give the second half of this. In general, got warm water near the surface, and at depth in the ocean, it's actually quite cold. Like down about 200 meters depth, temperature of the ocean in the equatorial region is only about 14 degrees Celsius, 12, 14 degrees Celsius. When that cold water is close to the surface, it's cold in the equatorial Pacific, and in general, the equatorial Pacific is colder on the equator than it is on either side of the equator because the dynamics of the ocean are such that cold water is constantly being brought to the surface. When an El Nino event occurs, think about like a giant bathtub here. If you were to like start blowing hard on the water in the bathtub, it's going to like pile that water up on one side of the bathtub. You have to blow pretty hard for a bathtub, but we're talking about the Pacific Ocean here, folks. So that water, the warm water ends up piling up on. In general, it's piled up on in the western Pacific because the winds are blowing toward the east. During an El Nino event, those winds relax, and that water kind of sloughs back off towards the eastern Pacific, distancing the surface from that cold water. And so that constant mixing that's occurring on the equator is now bringing warm water to the surface. And so we end up with a complete reorganization of the heat content of the equatorial Pacific. And we end up with that warming. It turns out once you warm in the eastern Pacific, it causes the winds to relax even more, which causes more warming, which causes the winds to relax even more. And that positive feedback cycle leads to the long-term development of an El Nino event. At the same time, there's another cycle that's delayed that shuts that off later on. And so that process, that growth process is what causes that. We're currently running models, so if you're interested in ENSO prediction, we have a model that's contributing to the International Research Institute, the sort of global ENSO forecast. Happy to talk more about that at some point.
We do have a question from a colleague who's at Pacific Northwest National Laboratory online watching tonight. He asks, where do you see the most need for greater investment of resources to support a community-centered, equitable, and just approach to building climate solutions?
Wow, good question.
You want me to repeat? I can repeat it if you like.
No,
Yeah,
it's it's only going to make me have to answer it more precisely. Boy, for investment, I'm a big fan of this model of collective impact organizations. And one of the biggest troubles that we have in collective impact organizations is funding the kind of infrastructure that you need in order to bring people together to come up with solutions. So that's a huge, that's an area that would benefit in general. Smaller communities especially are unable to afford, a large community like Seattle, there's all kinds of climate impacts work that's going on because they got enough tax base to be able to do that. But smaller communities are unable to do that, and so setting up organizations that allow that sort of thing to occur is a way towards developing equity, at least regional equity. Certainly, global equity is a different issue, and that would require. I guess I haven't thought much about that, so I'm not gonna offer opinions on that. I'd give you ill-informed.
Fair enough. Yeah. One more over here.
Thank you again for such a great talk. I'm curious, you mentioned a couple times the idea of like lifestyle and mindset within your presentation, and so I would just love to hear on like the personal note for you and your family with your 3 kids. Mm-hmm. What are some of those lifestyle choices that you've made to make that drop in a bucket impact, modeling a lifestyle that is maybe let go of some of those less sustainable practices? What would you impart on us as far as easy habits so we can help our neighbors adopt as well?
Yeah, I'm a big fan of the one-time decisions that you can make that have an enormous impact down the line. So we live in an area that we moved to our house because we could walk our kids to school every day, and I can bike to work daily, even when it's -6 out in Wisconsin. I got studded tires on my bike, and when it gets that cold, you just got to put some ski goggles on and cover all the skin. Otherwise, you get these ice cream headaches as you try and bike in this kind of weather. If it gets really cold, the grease on your chain, actually the freewheel locks up, and you have to continue to pedal the whole time. Otherwise, your chain keeps going. So that kind of stuff. I bike a lot. As soon as we could. As soon as the local power company provided an opportunity to get your power from green sources, we started investing in that. We started paying into that. So all our energy comes from renewable resources there. Again, you try and, these one-time things where you do it and then, it sticks for a while. If you're changing out we're a little more limited in Wisconsin just because it gets so cold in Wisconsin that heating requirements are almost every house in Wisconsin has natural gas heat, and that would require a complete retrofit of our house if we did something like that. So that's not so centralized heating when that gets replaced, we'll have to think about how we would do that. But the other thing, the kinds of things that are big solutions are things that you might not expect, so diet is a big one. and we're eating a lot more. My wife is a fantastic cook, to my detriment, and she has started, we're starting to do a lot more vegan meals, and it's fantastic. I mean, there's all sorts of fantastic foods, especially in Dane County, which has one of the highest concentrations of small family farms in the country. In the summertime, you can go down, any day of the week, there's probably 3 farmers markets around. You can go down and get. So, eating habits, eat more vegetarian, more vegan options there. A lot of the things that make a big difference are, just taking a big step back. What are some of the biggest things that we can do to improve our situation here? One is changing refrigerants. That's not something that all of us are going to do, right? I mean, that requires an industry shift. Educating girls in developing countries is one of the biggest things that we can be doing to reduce climate change. And the secondary benefits of that are enormous. So things you don't expect all the time. So take a look at Project Drawdown. Project Drawdown is a great resource for just hundreds of different solutions and documenting how those solutions might be. Might affect.
Thank you so much, Dr. Vimont. Let's thank him again for a wonderful talk. I really do enjoy the connection between, the complex systems and Jesuit education. That was a really cool connection. Did you enjoy that as well? I mean, it's really interesting to reflect on the way that we approach education in this context and how it informs your work. And so it's just sort of cool. I imagine that Professor Concatenator is very happy to see, our Gonzaga students going on and doing really cool things in the world. So thank you for coming and being with us tonight. And I hope to see many of you again at one of our talks soon.
The last thing I want to say with respect to that, and I'm going to get the last word in here, is that when I saw the Gonzaga Climate Institute was going to be a thing, I was like, wait a minute, what's this? We got a philosopher here who's going to be running the Gonzaga Climate Institute. And I got online to listen to the first one of these where Professor Henning outlined this. And immediately he started talking about the connections that we make and the changing mindsets. And all of this resonated so well with my experience as a climate scientist and thinking about how we as communities address this. Since then, I've looked at what the Climate Institute has done here, this Beat the Heat program, development of K-12 education, the research that's being done on looking at impacts of fires and smoke. All of this is cutting edge, and it is extremely exciting to see that. I'm very excited to be here and be able to present in this, and I look forward to engaging with the Gonzaga Climate Institute as you move forward as well. So kudos to just a fantastic effort. Thanks, everybody.